Hi. Dennis Rodman used to play basketball in the NBA. Now, he might not have been the world's greatest thinker, but he did say something quite fascinating, quite deep and intellectual about chemistry. What did he say? I'll tell you at the end. Between now and then, though, we need to talk about chemical bonding. Now, first of all, we need to understand about bonding. Bonding is so that atoms can achieve a stability. Now, what does a stability mean? Well, for us, it's going to mean a lower overall energy. We can also think of it as atoms achieving a stable octet, although stable octet will not always happen. There are some atoms that simply cannot get a stable octet, although they'll have their own little version of it, I guess. And there are other atoms that can actually go over the stable octet, and for them, that's actually quite a stable arrangement. The best way to think about it is that atoms bond to get a stable or a favorable electron configuration. That word right there. Let's try that again. That word right there, configuration, becomes an important one, although for us it means the same thing as arrangement. There's a couple of ways they can achieve that stable electron configuration. One way is to lose electrons or gain electrons, and the other way is to share electrons. And we're going to look at each one individually. We're going to start out with, first of all, deciding how do we know if it's a transfer, a loss and a gain, or a share of electrons. Well, that depends on a few factors, including ionization energy and electronegativity, which is perfect because we just learned all about those. Now, I want you to think for a second, just take a moment, remember what ionization energy is, think about the trend, remember what electronegativity is, think about the trend. All right, here we go, ionic bonding. Now, we know that ionization energy was losing an electron. Is it related? It's related, but an ionic bond is a little bit more complicated. It occurs between a metal. What do we know about metals? Well, metals have a low ionization energy, and that means that it doesn't require a lot of energy to remove an electron. There's our definition of ionization energy. But metals also have a low electronegativity, which means they don't attract electrons all that well. Okay? And they can achieve a stable octet by losing electrons. Now, I should have the word electrons there. But that's the easiest way for them to get a stable octet, is to lose electrons. It also occurs between a metal and a nonmetal, so there's the other half of it. And the nonmetal has a higher electronegativity, and that means it's able to attract electrons to itself. And they can achieve a stable octet by gaining electrons. So it looks like it's going to work out perfectly. One thing is able to lose electrons easily and gets a stable octet by losing electrons, and the other thing attracts electrons and gets a stable octet by gaining electrons. Sounds like a match made in chemical perfection. If we think about nomenclature for a second, because we've dealt with nomenclature but not really in connection with bonding, but let's connect it. Metals, we said that they're always positively charged in compounds. And we said that nonmetals are always negatively charged with metals. And we broke it down into more detail than that, but the basic of that was metals were always positive. Nonmetals, if they were with metals, were always negative. A positive charge, the word for that is a cation, and that happens when there's a loss of electrons. So what happens is metals become positively charged by losing electrons, and then they will form compounds. Negative charge, the word for that is an anion, and that happens when an atom gains an electron, or more than one electron. The other thing we said in nomenclature was that the total positive charge, that's the electrons lost, equals the total negative charge, that's the electrons gained. That should make some sense, because if I'm going to lose electrons, they have to go somewhere. If I'm going to gain electrons, they have to come from somewhere. So let's go back to the ionic bonds and figure out how the bonds form. I have here an atom of sodium. Sodium has its 10 core electrons. It has 8 in the second orbit, and it's 1 valence electron here. Chlorine, on the other hand, has its 10 core electrons, and it's 7 valence electron. So I look at that and I say, well, sodium has a stable octet +1, and chlorine just missed it by that much. It's almost a stable octet if it could just have 1 more electron. Well, that's what's going to happen, of course. So sodium doesn't hold on to its electron very well. Chlorine attracts it. the amount of energy required to pull this electron away isn't all that large, so chlorine is able to overcome that and attract the electron away from sodium and pull it onto itself. We start out then with that electron transfer. Well, now you'll notice what happened. That third energy level in sodium is no longer there. It's still possible, still available, but it's not occupied. So it ends up becoming a stable octet by losing that third energy level. Well, now I have positive charge on sodium, so now I have a sodium ion and I have a chlorine ion, which I would then call a chloride if we make one more connection with nomenclature. I've got opposite charges. Opposite charges attract. Those two ions come together and stick. There's no actual physical bond. There's no overlap. There's no connection. There's no tie between the sodium ions and the chloride ions except the opposite charges attracting one another. And if I look at a structure of sodium chloride, they form, or any ionic compound for that matter, but this one is sodium chloride, they form what's called a crystal lattice. And crystal just means it's a solid with a particular structure, and lattice refers to a very regular structure. The purple circles here would represent the sodium ions, and the green circles would represent the chloride ions. Now you'll notice that in this solid, I've got a positive alternating with a negative, alternating with a positive, and on it goes. My positive charges are as far away from each other as possible. My negative charges are as far away from each other as possible as well. If I look at the sodium here in the middle, it is surrounded by one chloride on top, one beside, one below, one on the other side, and we are in 3 dimensions. So there's one behind it, you can kind of see it back there, and if I had more layers in front, there would be one in front of it. So if I do the full count, I've got one sodium atom surrounded by 6, 1, 2, 3, 4, 5 back there, 6 which isn't shown but could be in front, 6 chloride ions. If I did a similar thing for my chloride ion, it has 1, 2, 3, 4 sodium ions that I can see. There would be one above it that's not shown, one in front of it that's not shown. Each chloride ion is surrounded by 6 sodium ions. So because of that, and because of the fact that I don't really know which ones pair up, which ones belong to each other as such, I don't talk about sodium chloride, and this is true for other ionic compounds, I don't talk about them as molecules. We refer to them as a formula unit. And what the formula unit is the lowest ratio between the total number of sodium ions and the total number of chloride ions. So if you think back to nomenclature, what we were doing was a crossover and reduce. So it's the lowest ratio of atoms, ions, in that particular compound. The other type of bond is a covalent bond. And a covalent, well, the word co, or the prefix co, means with or together, or things like that, if you think about co-workers and cooperate. And valent, well, that's where we get the word valence. So I'm kind of like together, valence, sharing, valence. You'll start to see why it makes sense in a minute. That is the result of 2 nonmetals combining. Now, if we back it up and think about nonmetals for a minute, both nonmetals are going to have a fairly high ionization energy, which means they don't lose electrons all that easily. They're also going to have a higher electronegativity, which means they both are doing a pretty good job of attracting electrons. So neither one wants to give them up. Both of them want to attract them. So they end up sharing the electrons. And they're going to share the electrons in pairs. And this is going to be kind of important, not so much now, but a little bit later. Pairs of electrons. They're going to share enough electrons so that both end up with a stable electron arrangement, which a lot of the time will be a stable octet, but not always. So we're going to stick with the stable electron arrangement, whatever that happens to mean. So let's go back to some Bohr diagrams and have a look at this. So I've got chlorine atoms here and chlorine atoms here. Both have a high electronegativity, both have a high ionization energy, both have 7 valence electrons, both are 1 short of a stable octet. If I bring those 2 atoms together and they attract one another together so that they overlap their valence orbit, covalent, sharing of the valence. If we overlap and share those electrons, now those electrons are going to spend part of their time with the chlorine atom on the left and part of their time with the chlorine atom on the right. So they're sharing those electrons. When we talk about covalent bonds, we then talk about a molecular compound. You've probably heard the term molecular compound before. So now we're talking about individual molecules. These are their true molecules. So when I write, say, for example, H2O, that's almost the recipe. That means I've got 2 atoms of hydrogen, and if these were a water molecule, then I would have 2 atoms of hydrogen and 1 atom of oxygen. So my chemical formula represents the actual molecule that I'm talking about. And then the formula unit, and again, I don't need to use the word formula unit, but I could, it is an independent thing. So a sodium chloride, NaCl, is not, because in a solid structure, I've got lots of each, and then I write the lowest formula. I don't do that for molecular compounds. Whatever the formula is, that's what the molecule is. And these are the true molecules. Now, I want to leave you the parting question, and I haven't forgotten about Dennis Rodman. Is there anything in between an ionic bond, or an electron transfer, and a covalent bond, where there's an electron being shared? Electrons being shared, we should have. Is there anything in between? Can there be some kind of middle ground? All right, back to Dennis Rodman. Dennis Rodman said about chemistry, he said, chemistry is the subject you take in high school or college where you learn that 2 plus 2 equals 10 or something. That's not part of this course. Maybe that's the college one. Anyway, I don't think Dennis Rodman took chemistry. He should stick to basketball, or actually, lately, he's been the goodwill ambassador in North Korea or something like that. Anyway, we'll see you in class. Talk to you later.